Hello. Welcome to Calculus 3, class number 5, part 1. Part 2 is going to be lab, so this is going to be a shorter stream. We are only covering one section tonight, which is on curvature and normal vectors. I already mentioned at some point in this class that we are going to learn about curvature, which will be a way for us to quantify the curve, whether it's straight, bent a little bit, or really bent. The curvature is numerical value computed at the point at the curve somewhere where you're interested in curvature. We are going to start building it from the unit tangent vector and so on, but there are 3 different versions of that formula. We will use one of them. You will remember one of them. Didn't you vote for the test to be some point? When is the Wednesday exam? Okay. So exam is on Wednesday, covering chapter 11. You have those quizzes going on, so make sure you are solving those quizzes every day. They're opening at 6 a.m., as some of you might not know, and close at midnight every day. So after the class, you will still have about an hour and a half to finish today's quiz. One of the quizzes had the partial derivatives on it, which is, I believe, 12.4 or something like that. But partial derivatives are the same like regular derivatives, where you keep y constant if you're taking derivative in x. So you would just be dragging y along. And any term that does not have x's and has y's, if you're taking derivative in respect to x, is just 0. So, and the same thing when you start taking derivative in respect to y or z. So those should be fairly simple for you guys to do, even though we didn't have the official lecture. When we have official lecture on it, we'll see application of that and so on. The problem you experienced probably was just mechanics of take the derivative and move along. So it's technically a calculus 1 question. Then I have no clue how that ended up there, but you can manage it. It's not a big deal. Oh, curvature, yes. Unit tangent vector. Unit tangent vector with a hat was the derivative of our vector r divided by the magnitude of vector r, and we know that that was the velocity divided by the magnitude of velocity, because r was the vector valued function for position, and then the derivative of that would be velocity, the derivative of that would be acceleration. So the curvature is defined through the arc length parametrization in terms of s, arc length s. So it's parametricized, but we can't compute that way. So the definition for the curvature is going to be one thing, and then you guys will have a formula that you will remember to compute curvature. So first we go with the definition. And again, this is not the way to compute things. Let R of t describe a smooth parametricized curve if S denotes the arc length and T hat is the unit tangent vector the curvature k of t is given as the derivative of the unit tangent vector in respect to the arc length, and then we take the magnitude because it is a scalar quantity. So this is only used to describe the concept. We don't compute things this way. I already said that. So here is a curve, and let's say over here I have the unit tangent vector at this point. How do we measure change? We take the derivative, right? What should be the curvature? The curvature should be of how fast this vector t is going to change in its immediate neighborhood. So when you have something over here, you see how quickly vector t changes, right? And over here, not so much for the points that are relatively close by. So when you're looking at this, the curvature, let's call this curvature K1 and call this curvature K2. We see that K2 curvature is bigger than K1 curvature because the curve on K2, the bottom picture, is more bent, right? The curve is more bent than the one on top. So a very simple idea to quantify the curvature. All we need to do is to take the derivative in respect to arc length. But that's not how we calculate, so we immediately write the theorem. In your book is theorem 1110, but we're going to call it curvature formula because that's how we compute. Curvature formula, and the curvature formula k of t is going to be the derivative of the unit tangent vector divided by the magnitude of the velocity. So this is how we compute. This is the formula we compute. If you're interested in the derivation of this, parametricizing the arc length, writing it as dt over ds times 1 over, sorry, 1 over dt, and then separating the two things, you get the velocity on one end and it's a two-step procedure. It should be in the book. Yep, it's in a book on page 842. You can quickly look into that if you're interested. So let's take a look at the curvature. First of all, it should be common sense that straight lines have zero curvature because they're straight. And the circles should have a certain kind of curvature, so we can compute those. I'm going to compute the curvature for the line, and then I will challenge you to compute the curvature for the circle of arbitrary radius r, because you know how to parametricize that and get everything sorted out. Let's take a look at the straight line first. So straight line curvature, or curvature of the straight line. We need to have our vector r. We can do this in 2D or 3D, it doesn't matter. Let's do 2D because we're lazy. We have x0 plus at, comma, y0 plus bt. So that would be our two-dimensional parametrization of the straight line. And now we have, that's our r. From here we can compute r prime immediately. R prime is going to be just ab, because we are differentiating in terms of t, x0 and y0 are constants. Those are numbers, the point. And we can create our unit tangent vector immediately by using our AB and dividing it by the magnitude, which is that. So now we have the unit vector. Observe there are no t's anywhere, right? So now the curvature, if you remember at all, was the magnitude of the derivative of the tangent vector divided by the r prime of t. And what's the derivative of unit vector in this case? Yes, Mary. Why is it 0? No t's, right? A and b, they're all constants. So we have 0, 0 divided by the magnitude of a squared plus b squared, which is, and all the magnitudes, right? It's 0, which makes sense. Straight line has a 0 curvature. Curvature of a circle. Go. You know what the parametrization for circle is. You better know, otherwise you're doomed. And then get your unit tangent vector, get everything. Let's say that the circle has the radius capital R. So we are doing this for all possible cases. So capital R radius for the circle. For the circle, you can just center it at the origin, so it's not annoying, right? So you can just use origin. You don't have to shift it anywhere. All right. That was sufficient time. The answer is 1 over r. Let's, as Nike would say, just do it. So parametrization for the circle radius capital R is going to be vector valued function r of t is given as r cosine t, r sine t. So those are our x and a y for parametrization. We immediately need r prime of t, which will be negative r sine t, r cosine t. Then we find t hat by dividing the r prime, which is negative r sine t, comma r cosine t, by the magnitude of this, which will work out to be r after an hour of writing the same thing over and over again. So for this one, we factor out r, and then you have a square root of sine squared x plus cosine squared x, which gives us 1, so it's just r. And then that r will cancel with r's on top, so we get in the numerator, so we get negative sine t, comma cosine t as our unit vector t. To find the curvature, we have to find the derivative of this vector, so we find the derivative of vector t, which will give us negative cosine t, comma negative sine t. And finally, curvature is given as the unit tangent vector, the derivative of unit tangent vector magnitude. Magnitude of the derivative of the unit tangent vector, there we go, divided by the magnitude of the derivative of the vector valued function, which is our parametrization. There we go, much better. Now we already know that this is r. The unit tangent vector would be the square root of negative cosine t plus, well, squared, plus negative sine t squared, which is 1 over r. Yay. It's done right here, the same calculation. You factor out r squared. When r squared escapes the square root, it just becomes r, and now what's left under the square root is sine squared plus cosine squared, which is 1. Square root of 1 is 1. 1 times r is r. Perfect. Yay. I know I said it a little bit too fast, but you can play it at half a speed. If you watch it again, and then I'm just kidding. That part you can speed up. All right. So we have the curvature of a circle. And as I said, there is this third formula. We're not going to use it, but there is a third formula that utilizes the cross product. Much more painful to compute, right? So if you like pain, I mean, you can remember this one and then use this one rather than velocity cross acceleration divided by the velocity cubed, magnitude of velocity cubed. Yeah. No. Yeah. You're hopefully gonna do the t hat prime divided by r prime and be done in 30 minutes rather than doing this for an hour and a half.
Would it make a difference? Would it make a difference if you do a times b, well, a cross product b?
But what is the limitation, guys, of this formula? What's the limitation of this formula? It only works for 3D. It's a cross product there, right? So can you solve the problem we just did with this? Oh, Mary.
You can cross 2 and just say z is 0, right?
When you do it with zeros, you get zeros all over the place. You can't do the problem we just did out of box. If you invoke the other one with the zeros everywhere for z, with that modification you can. All right.
So this formula only for Sweden.
Yeah.
If we know the x1 was the formula.
Well, they have an interesting. Okay, here's the quick example. Try this formula. Why not? They have a quick example in a book that it's actually very fast, because t squared 10 negative 10. This can be done fairly quickly. Oh yeah. What happened? Oh, you figured it out? Awesome. The cross product. It's a quick example. With a quick mistake and a quick fix, and move along. Good enough. Okay. So the next concept is the principal unit normal vector. So we know that the curvature will tell us whether the line is straight or curved, and then if the line is curved, it will quantify that curvature, and the larger the value, the more curve there is, and lesser values have a smaller curvature assigned to them. The unit tangent vector will show the direction in which you would continue. So it's a tangential, right? motion. So if you, let's say, lose traction, you continue moving down the tangent vector path. So the unit tangent vector shows the direction of motion, shows the direction of velocity, and it's tangential. The principal unit normal vector will show which way the curve turns. So if I have a curve, let's say like this, and this part over here is your tangent vector, the normal vector would be this way. And I'm also going to use the hat because it is the unit vector and the direction of the curve, right? Let's say this is the direction of the curve.
Always 90 degree.
Normal, 90 degree. So what is the formula? The formula is going to be the derivative of the unit tangent vector divided by its magnitude. Again, you will use the chain rule to change from parametrization through arc length into this formula. This is the formula that you will be using to compute. So you see how important the unit tangent vector is. You have to find that one, and then with that you can find curvature, you can find the unit normal vector, and these guys will be used further for other things. So note that the unit tangent vector is always perpendicular to the unit normal vector, and because of that we have that their dot product is what? Dot product is 0. Find principal unit normal vector. Punvo. Find the principal unit normal vector for helix. A cosine t, B sine t, no, sorry, A sine t, and then bt. There we go. Because the radius A has to be the same circle. If you put two different ones, then you get the ellipse. And a living nightmare to solve the problem at the same time. Package deal. Okay, have fun. You know how to find the tangent vector, you know how to find the derivative of the tangent vector, you know how to find the magnitude of the derivative of the tangent vector, and then put all of that together after a page of calculations.
I'm like, you know what you're talking about. Like you got the answer.
No, but it's so funny. Every day you make it like
I'm fine. I'm fine.
you always go into
Waving over the
However, you were right here. That's what I thought.
Wait, hold on. Do that out. Boil it out. There you go.
Myself,
There's no reason for derivative on the bottom. It's constant.
Oh, because there's no thing.
So you one over that is constant.
I like writing other things. It doesn't matter for math.
No, it doesn't. Because you have the A, B, and A.
No, it's not. No, everyone thought I should run.
It's like right over three. Then if you had what A is, like one and three was, then 4, 5, 6, 7, 8.
There's no need for proportional rules because there's
For the moment, I thought I'd be cube over here.
No.
it's not a portion. There's no E.
It's A squared plus B squared. Right? So they're not variables, they're parameters. Oh!
She's my homeboy. Don't be. it up a little bit. White it up.
It's a constant. Yeah. I go by schools. I get to when I gotta go to attend. Then it's whatever the hell is over there. Once you suck into something. I gotta hang out more with you. They're so only going there next time. Because I spent about all I knew about it was they said, oh, you can go over there, then you come to the computer and the computer will take care of it. Yeah, and we all well, apparently I'm seems it. All I get when I get there is like, oh yeah, you can buy.
Alright, here, I got this.
They probably see my size and they say, hey, what human size shirts. I'm pretty. Just because you brought it up, I'm like, alright, and we'll take it. No, not your manager.
All right, guys, let's take a look at this problem together. So find the principal unit normal vector. So we start with r prime, which is negative a sine t, a cosine t, and then just b. And then we are going to take this and create a unit tangent vector. unit tangent vector is going to be r prime divided by the magnitude of this. Now the magnitude of this, I walked around and I looked at your work and I saw that it's a squared plus b squared, which is correct, because the sine and cosine square, when you factor out a squared, they will give you 1, so you just end up with a squared plus b squared. So it's a square root of a squared plus b squared. That's what we have for the tangent vector. Now, please understand that a and b are both parameters, like constants. So derivatives apply only on sine and cosine. So the t hat is going to have the same denominator because it's a constant that we rewrite. When you're taking the derivative, you rewrite the constant. And then derivative of the top is going to be the derivative of sine t is cosine t, so negative a cosine t, comma, negative a sine t, and then 0 at the end, because the derivative of b is 0 in respect to t. So now we have this. And now we're going to need to find the magnitude of this. And to find the magnitude of this vector, we will have to break this into a vector times the constant over here. So you can think about it this way: a squared plus b squared times the vector negative a cosine t negative a. So sine t and then 0. So to find the magnitude of this vector, we have 1 over square root of a squared plus b squared. And then we have the magnitude now, which is the square root of a squared cosine squared t plus a squared sine squared t, and then plus 0 squared if you really have to have that. So the magnitude of this one is, as you can see, a squared square root of that, which cancels down to just a, over square root of a squared plus b squared. It's not 1. Why? It's not 1. Why? Yes. Yeah, but I know, but it's not 1. Why? Is this a unit vector? Is this a unit tangent vector? No. What is it? It's the derivative of unit tangent vectors, so it's not length 1. That's why. But now when we put them together, they become the unit tangent vector, the unit normal vector. So that's something you have to be careful about. So I will. So we have negative a cosine t, negative a sine t, and 0 divided by the square root of a squared plus b squared. All of that, so that's our t prime, t hat prime, divided by the magnitude, which is a over square root of a squared plus b squared. And then these guys cancel. and I get a normal unit vector of t. Now A will cancel all of these, so all I get is negative cosine t, and then sine t, and then 0. That's what I said. Please pay attention. Clearly negative, right there. Look. You see? Right there. So let's take a look at this calculation one more time. So find the principal unit normal vector for the helix. And this is the general formula for the helix, where you have the radius of the circle, which is the base of the helix, and then the linear rise bt. So depending on how much b is, whether it's going to rise faster or slower, but it's going to rise at a constant, right? It's going to rise at a constant pace. So now helix is given, and that's our vector valued function r. We find r prime, we find the tangent by dividing r prime with the magnitude of r prime, which is the velocities, and we get the unit tangent vector. So now unit tangent vector is given as this. We are supposed to take derivative of it, since a squared plus b squared here is the constant. We get to copy that. So 1 over a squared plus b squared is copied times the magnitude of the vector t prime, which is, when you square this, you get negative a times negative a is a squared, cosine squared plus a squared, again sine squared, and then 0 squared. So now what happens here is, don't worry about the 0. You factor out a squared, and then it escapes the square root, just becomes a. Under the square root, the only thing you left is cosine squared plus sine squared, which is 1. So you are left with a over the square root of a squared plus b squared. All we need to do from that point is to write the unit normal vector as the vector t derivative of the t unit vector. There we go, tangent vector, which is both of these divided by the magnitude of the derivative of the unit tangent vector. These guys will cancel, and then a will also cancel these two a's, and you are left with the answer. Don't forget comma 0 at the end, because it's 3D. And we have the unit normal vector. Does this make sense? Of course it does make sense, because we have, if you have the helix, these unit normal vectors will always point inside of the helix, which is in a direction in which the helix bends. And that takes care of this. That takes care of this lecture.